Okay guys, let's have a little look at the intro for this section here then. I've written that down, basically the essence of all the ideas we're going to look at here. We're going to start with gradients and slopes, and I think that gradients is quite good. So if you take a Cartesian axis, right, so let's do that. Well, the first thing I want to say though is a gradient. If you're walking along a hill or you're driving a car and you see this sign, and it's probably maybe written as, this is written as a ratio, but sometimes it's written as a percentage. But basically you see that and you're walking up a hill. There you go. I'll draw a little picture of you. There you are. And you're walking along. And you see this sign. It tells you how steep the hill is. If you're driving your car or walking along, you'll see this sign. It means you've got a 1 in 3 hill. What does that mean? Well, it tells you the ratio of the steepness. So basically it's saying for every 3 units horizontally, you're going to go up 1 vertically. And it tells you the measure of the slope. So for example then, that's a 1 in 3 hill there. I've just done a little sketch up for you. But let's do another one. Let's do, say, a 1 in 5 hill. Okay? So if you saw that signpost, a 1 in 5 hill, it would mean for every 5 steps, so to speak, horizontally, you go up 1 vertically. And there's your 1 in 5. That's your hill that you're walking up as you go along. Quite a shallow incline, a shallow gradient or slope. So can you see which way round it is? This is a 1 in 5. In terms of the mathematics and using Cartesian axes, the 1 in 5 here we write as a slope of gradient a fifth. That's the way around we write it. So the amount you go up you put on top, the amount you go along you put underneath, and it's a 1/5. That's how we describe it. So that's a 1 in 5. So let's draw another hill now, another little, just so that we're absolutely clear. So if I said to you, you're walking along the hill and you saw this sign, right, which is here, and you've got a 3 in 1, and you're driving your car, you're walking along, you see a 3 in 1. That means for every 1 you go along, you go up 3. You've got to get it round the right way. This is a 3 in 1 hill here. Now you're not going to be driving your car very fast up that, are you? And you're probably going to need crampons if you're going to try and get up it yourself or by yourself and climb it up, because it's a significantly steep slope. So that gradient then, remember we said that the number that we go up goes on top, the number we come across goes underneath. So that's of gradient 3. So it's very careful to get the arrangement round the right way. And if ever you forget, remind yourself with this little visual picture of the 3 in 1 hill or a 1 in 3 hill. So the 1 in 3 hill, as we mentioned at the outset, would be you go along 3, that number is the amount you go along, and this is the amount you go up. So that one's written second and the other one's written first. So there's your 1 in 3 hill. So when you see a 1 in 3, you know you've seen it, and it tells you, now you know which way around it would be, because it cannot be a 3 in 1, because you're not going to be able to go up that very quickly anyways. Okay then, so that notion then, so the 1 in 3 hill was of gradient third, the 3 in 1 hill was of gradient 3. So with that thought in mind then, let's have a go. Let's just draw a picture then for gradients on the Cartesian axis, because it's the same, basically the same picture. Here's the O, here's X, the positive forwards direction, here's the forwards upwards direction, and in a sense you're here. There you go. And you're facing in the forwards direction. So any slope between 2 points, say these 2 points, will have a gradient. So you can picture yourself in your mind's eye as though you're on a hill with a slope. This is the amount you go up, and this is the amount you go across. So the slope here would be this height over this length here. That would be a measure of the gradient or the slope. So let's do a practice example then. Let's suppose we have the slope, the coordinate 1, 1 here at the bottom, P, and the slope for Q, what we'll do is we'll do 2 and say 1.5, shall we? 1.5. So let's work out the gradient of that slope then. Remember what we said, it was the increase in y. So I'm writing out the formula now. The amount you go up divided by the amount you go across, increase in x. And there's the formula there for the gradient or the slope. So here, the increase in y, so I'll just snick it in under here. The y difference would be 1.5 to 1, which would be a difference of 0.5, divided by the increase in x. Well, it goes from 1 up to 2, so that difference is 1. So 0.5 divided by 1 is 0.5. So this has gradient 0.5 then. Shallow positive gradients. So that's that line. So let's have a look at another line now. Right, now we've got our formula and see how we interpret other types of slopes. So let's suppose we have a slope just like this then. Okay, suppose we go from here to here. And there's P, and let's call that 1 and 3. And let's do Q, which is, let's say that be 4 and 2, suppose. Just suppose. Right, and there's Q. Okay, what's the gradient of this slope? Well, we said it was the increase in y divided by the increase in x. So in practice, what you do is you just draw a triangle either underneath or on top, it doesn't matter, because then you can read off the differences in these increases. So the increase in y here would be you're at height 3 and you go to a height 2. So the increase, you're going from 3 to 2. It's a negative increase. You're actually going down 1. So the increase is minus 1. And then the increase in x, you go from 1 to 4. So the increase in x will be 3, won't it? You're going across 3. So you're going down 1 and across 3 minus 1/3. So it's a negative gradient. And it's a shallow negative gradient because it's not very steep, is it? So that means you're going downhill. A negative gradient means you're going down. A positive gradient means you're going up. This is shallow. So I hope that notion of gradients then is fairly clear. It's always good to picture in a concrete framework of thinking of yourself on a hill, looking at, say, a signpost, which reads 1 in 3 hill or 3 in 1 hill. And then you're less likely to make a mistake getting it the wrong way around. So basically, gradients then, this would be a shallow positive gradient. As you get steeper, the gradient will increase in magnitude, all right? And then you get down to a shallow positive gradient here. This line here, which is a flat line, there's no increase in y. So whatever the increase in x, you can draw a triangle in your mind's eye. So there's your triangle, you see. This little y distance is 0. The x distance, you could say, is 1, for example. And so the gradient would be 0. So a flat line has gradient 0. So that's important to be happy with. And then when you go through 0, you're going to go negative. So you're going downhill now. And it increases, the value of that will increase in the negative sense. All right? So positive slope, negative slope. And they describe basically all this sort of slopes of lines that you'll ever see on the xy coordinate axes. So I hope that's clear for gradients then. I hope you've got some sort of intuitive notion and orientation. Don't forget, on your axes, that you're always facing forwards in the positive direction. That is the positive forwards direction, and here's the upwards direction. That's the way around the Cartesian axis is written. So that leads us on then. Now we know what gradients are, a clear understanding of that. Parallel means that two lines have the same gradients. So it could be any sort of gradient, but as long as the next line to it has the same gradient, then they're parallel. Perpendicularity. Two lines are said to be perpendicular. If we can, there they are there. They don't have to intersect, but they, well, they would intersect anyway, wouldn't they? But they're perpendicular means they're 90 degrees between them. So again, any orientation of lines, as long as there's 90 degrees. Now, if we had the gradient of this line here was m1, say, and the gradient of this line here we found to be m2. In this instance, this example, m1 is positive, m2 is negative. And what you get for the property of perpendicularity is that m1 times m2 equals minus 1. So that's a property of gradients when they're perpendicular. So we can use that as a check to make sure that we get two lines being perpendicular. Okay then, so that's that done. Oops, that's minus 1. Right, that's that done. So that's perpendicularity. So again, right angle triangle. Again, a right angle triangle means two lines in the triangle will be perpendicular to one another. So again, if you just have a triangle in Cartesian space, say one that looked like that, ABC, and you'd made a sketch of it like so. If you could show, and these were the coordinates of the triangle, if you could show that this gradient was the line AB was was times by the gradient of the line BC was minus 1, then you'd obviously clearly have a right angle triangle. Isosceles, two sides of the same length. So here you don't have to worry about two. So here's our isosceles triangle. See that side there is the same length of that side. So how can we show that a triangle is an isosceles triangle? Basically, the best way to do it from the point of view and the context of the questions we're doing here is you just work out the length of line AB and you work out the length of line AC. And for an isosceles triangle, two sides of this triangle must be equal. And if all three sides are equal, then we've got an equilateral triangle. So that's also something worth mentioning here. Oops. Okay then, so equilateral triangle, isosceles triangle. Collinearity is the only other thing I wanted to briefly mention. So I'll just quickly mention that. And just tidy this up a bit. Collinearity, well, it's self-evident what it means. Basically, what you'd need to show, if you had 3 points A, you had a point B, and you had a point C, to show they're collinear, you'd need to work out one way to do it. If you wanted to show that AB is collinear to BC, okay, you'd work out the gradient AB, and because B is connected by a line here, you could work out the gradient BC, and they'd need to have the same gradient. Because these lines AB and BC have the same gradient, and they're connected at the point B, of course, then clearly they're along the same line and they're collinear. The other way you could do it is you could look at AB in the first instance, and then you could look at AC, and then clearly the line B segment BC will then also be collinear to AB. So you can choose which way you'd like to do it, and there's some questions on that as well. So okay guys, I hope I've just quickly gone through some of the notions that we need for this section, and again it's fairly well explained in the examples, I would hope, as well. Okay then, catch you in the next section then. All the best for this one. Cheers.